Hello everybody, welcome to online class Microprocessor Architecture. In this video lecture, we will try to understand the microprocessor architecture in detail. So, I made this topic of microprocessor architecture in 2 or 3 videos so that people may not feel bored and you will understand it clearly. As you know, in the earlier video, a microprocessor is a large-scale integrated chip which performs various arithmetic logical operations. And you also know that when I say very large-scale integrated chip, it is of very small size. But to understand the working and its efficiency, one has to know the architectural features of the microprocessor. Now let us start the lecture microprocessor architecture. When you consider this microprocessor, all of you know that to understand this basics of the microprocessor, in the earlier class itself I have told you we are considering here Intel 8085 microprocessor, and this microprocessor is also known as the central processing unit. When you consider the salient features of this 8085 microprocessor, it is an 8-bit device with a clock speed of 3 to 5 megahertz. Here I wish to tell you one interesting thing. The minimum frequency that is required for the operation of a microprocessor, 8085 microprocessor, is at least 1 megahertz. But someone may ask the question, sir, why should not we use only 1 megahertz? The problem is, if we use 1 megahertz frequency instead of 3 to 5 megahertz, the performance of the microprocessor, especially the speed of execution, may not be sufficient. So the optimized values are either 3 megahertz or 5 megahertz. There are some versions which are 3 megahertz, as I have explained in the earlier video, or some are 5 megahertz. And as you know, the microprocessor is a programmable device. So it should have some instructions to program this device. So the 8085 microprocessor supports 80 basic instructions, and these instructions are normally represented in opcodes, operational codes, because the 8085 microprocessor itself, in those days, it was not supporting the high-level languages like C. Therefore, people used to use the assembly language programming. So to enter the program, we used to use operational codes. Once it is working at 5 megahertz means what will be its time period, time of execution, 1 by 5 megahertz, and this will be 200 nanoseconds. 1 by 5 megahertz, you can easily calculate 1 by 5 into 10 power 6. Yes, I am able to write this. Okay. So 10 to the power of 6 means, so 1 by 5 is 0.2. 0.2 into 10 power minus 6, otherwise 200 into 10 to the power of minus 9, otherwise 200 nanoseconds. So a microprocessor of 5 megahertz operational frequency will have an execution time of 200 nanoseconds. It means it can execute a single instruction in 200 nanoseconds only. This is the important thing. Also, you know that 8085 microprocessor is a 40-pin dual inline package chip which works at plus 5 volts DC. It has one 8-bit data bus. In the earlier class I have explained to you, data bus means group of lines which carries the data, and 16-bit address bus. 16-bit address bus means, so this is address bus. So 16-bit address bus means, what is the meaning of this? It carries an address of how much? 16-bit wide. That is the most important thing. So this is 16-bit address bus and 8-bit data bus. ADRESS, address bus. This is the most important thing. So this is, you can forget about this, it's a mistake. 16-bit address bus. Here I have written. So once you have a 16-bit address bus means it can access an address space of 64 kilobytes, that is 2 power 16. Once it has a 16-bit address bus means it can access an address space of maximum 64 kilobytes. That's another important thing. So, and another thing, it has one 8-bit status or flag register. It is also called either status or flag register, where there are only 5 flags. There are only 5 flags, that is 5 bits of this 8-bit register are used. That is another. 85 supports a total of 5 interrupt sources, among which one is a non-vectored interrupt and other 4 are vectored interrupts. That means, so there are 4 vectored interrupts and 1 non-vectored interrupts. I will discuss this vectored and non-vectored interrupts in the next coming videos. So where the normal execution of the program, normal execution of the microprocessor is interrupted because of these interrupt sources. We'll consider this in the next video. Next, it has one 8-bit accumulator, one 16-bit program counter, and one 16-bit stack pointer register, and one 8-bit instruction register. The architecture of 8085 is memory-based architecture. Here I wish to inform all of you that you should remember that in the early days, the majority of the Intel processors are memory-based CISC architecture, complex instruction set computer architecture. That means the number of registers available in the processor will be less and majority of the instructions are memory based. That means the CPU has to fetch the instructions from the external memory. That is the most important thing. So majority of the instructions were also, that's why complex, it used to take more time. And another most important thing is this Intel CISC architectures are also accumulator based architecture. What is the meaning of this? That means majority of the instructions are based on the accumulator, or the instructions will work only on the accumulator. I will explain this in the next slides. So another important thing, the 8085 microprocessor has one serial port control, that is, which has 2 lines, that is a serial output data and a serial input data. So these 2 lines will help the user to send the data serially either into the microprocessor or from the microprocessor, that is out and in. Next, this 8085 is an enhanced version of its predecessor. Earlier microprocessor was 8080A. Then 8080A was improved and the 8085 was released. But the instructions are upward compatible. That means the instructions of 8085 or instructions of 8080 are compatible with each other. Another thing, 8085A has an on-chip clock generator with external crystal using either LC or RC network. This also we'll consider in the next video about the clock generator and about the clock frequency, etc. with some examples. The 8085 microprocessor in general is built with nearly 6,200 transistors. As I have told you in my earlier video, it is a VLSI chip, very large scale integrated chip. So it was designed with 6,200 transistors. Next, the enhanced version of 8080 is the Intel 8085AH. It is an N channel. It is a N channel. It's a mass technology. It is a N channel depletion load silicon gate. That is also H mass 8-bit processor. So next, clock frequencies of 3 MHz, 5 MHz and 6 MHz selections were also available in those days. So in the earlier video itself I have told you this 8085 microprocessor is no more available. It is obsolete, but only to know the information we are going through these lines. Understand the architecture. The best way is understanding the block diagram, considering the block diagram. If we consider the block diagram, the most important parts are sections of a 8085 microprocessor. Number one is ALU, that is arithmetic logic unit. So here you can see the arithmetic logic unit. That means it performs all the arithmetic and logical operations, because you know itself already that the microprocessor itself is a processor which will perform arithmetic, logical and control operations. So all the arithmetic, logical operations are performed by ALU. It is also called 8-bit ALU. That's why in the brackets you see the number 8. It has various registers. Why do we use a register? Registers are used to store the data temporarily. Registers are nothing but temporary storage elements. Actually, according to your digital electronics, you might have already understood that a register is nothing but a set of flip-flops or latches, because a latch is a single bit of or storage unit, memory unit. So that means if I want an 8-bit register, means I may use 8 latches. Each latch will store 1 bit of information, either 1 or 0. There are so many such registers. Here you can see what are the register: B register, C register, D, E, H, L, program counter, 16-bit, stack pointer, increment, decrement. Another most important thing is your accumulator. We'll consider these things one by one. Just now I have told you I have a serial I/O controller which will help to send the data either in or out from the microprocessor. And there is one interrupt controller. I have just now told you that it will support other than reset, interrupt. This is interrupt acknowledgement. It supports 5 interrupts, that is trap, RST 7.5, RST 6.5, RST 5.5 and interrupt. So we will consider in detail these things in the next slides. Next, third point. What is this third point? Timing and control unit. So here you find the timing and control unit with certain signals. It has its own signals. You should remember that is the clock. Similarly, clock in, clock out, control pins, status pins, DMA, direct memory access pins, and reset in and reset out pins. All these things. So here you will have under the control read write pins, address latch enabled. All these things we'll consider in detail. That's why I told you this microprocessor architecture will be explained to you in 2 or 3 videos so that you can understand clearly step by step. This is about the block diagram video. I will consider first ALU and some of the registers. In the next video, I will explain the remaining things so that you will understand clearly in detail. Okay. Now, first in the architecture, once again, let us know some more points. I tried to repeat some points which are missed in the earlier slides. Intel 8085 processor is based on CISC architecture. Very, very, very important. So when you go to higher classes, you'll understand that there is also another type of architecture that is called RISC architecture, where you have the ARM processors, ARM, Advanced RISC Machine, ARM processors and other processors of very high speed. So the processors nowadays which are used in your mobiles, that is iPhones, some of the laptops, some of the small devices, gadgets, they are all RISC architecture. So the Intel processors are mostly, as I have told you, repeatedly told you, majority of the Intel processors are CISC processors. Of course, nowadays they are also slowly changing to RISC processor architecture. So okay, now at present, the architecture of the 8085 microprocessor gives the details of internal arrangement, etc., which I have explained already. So now let us go to the first section of your block diagram, that is arithmetic and logic unit. The computer people popularly call this as ALU. So ALU means arithmetic and logic unit. So the ALU performs, as the name itself indicates, the ALU performs arithmetic and logical operations. What are these arithmetic operations? Addition, subtraction, complementing, logic, etc. And what are the logical operations? Logical AND, logical OR, logical exclusive OR, incrementing, decrementing, rotating, shifting, and clear. So these are all the various operations that you can perform using your arithmetic logic unit of 8085 microprocessor. That is the first thing. So it is basically an electronic circuit which can perform all these operations. That's why we say ALU is made of, remember, made of logic gates and adders, as you know already in your digital electronics. So the logic gates can perform OR gate, AND gate, XOR gate. They will perform various logical operations. And adders, binary adder, subtractors. So you have seen them in your digital electronics. So this is a combination of all these things. So ALU is a combination of various logic gates, the binary adders, etc. Now this ALU consists of 3 registers. So when you consider your block diagram here, you can see clearly that this ALU is associated with 3 important registers. You can see here. One is accumulator. This is associated with this. One next is the temporal register associated with this. This is flag register. All others are outside the ALU. That's why first we'll consider these 3 registers in this lecture. In this class, we'll consider accumulator, temporal register, and some of the flag bits of the flag register. All the 3 are EU-bit registers. That's why in the brackets I have written 8. In this video, in this lecture, we'll consider first these 3 registers. In the coming classes, we'll go to the other things. Arithmetic logic unit. What is this first one? Let us consider now the accumulator. So as I've already told you, what is this accumulator? It is an 8-bit register. Very important. Accumulator is an 8-bit register which is also treated as a special function register. It is a special function register. What is the speciality of this? That is, you come across in the next line. Most of the arithmetic and logical operations are performed using this accumulator register. Most of the arithmetic and logical operations are performed using this accumulator. Very important. All the I/O data transfers between 8085 and I/O devices, input-output devices, are performed via accumulator only. No other register will be helpful. Suppose I want to input some data in, that instruction will work only on accumulator. Suppose I want to use the instruction rotate, that instruction will only work on accumulator. Clear? Similarly, shift. If I want to use a shift instruction, this will work only on accumulator. Then someone may get a doubt. So how do we perform shift on a data which is on other registers? Then what we have to do? We have no other option except moving that data first into the accumulator, then performing either shift, either I/O operation or rotate operation or complementing operation, anything. This is the advantage as well as disadvantage. These things you will understand when you go to the higher level processors, which are, as I have told you, mainly RISC processors. These are all CISC architecture. This is, in the early days, Intel used to follow this architecture. That's why I have also told you this architecture is accumulator based architecture. An accumulator is nothing but an 8-bit register. So now let us come back to this. So one of the operands for arithmetic operations in ALU is from accumulator. While performing the arithmetic operations, one of the data operand will be in the accumulator only. Even after performing the arithmetic operation, the result is stored back in the accumulator. Remember, after, for example, add a comma b. When I have the instruction add a comma b, after adding the contents of a and b, the result is stored again in a accumulator only. So that's why the accumulator is also sometimes called a default register. Accumulator is also considered as default register. That means in some instructions we don't mention the destination. Even if you do not mention the destination, the compiler will understand that the destination is accumulator, or even you also have to understand that the destination is accumulator. For example, I write add b. What is the meaning of that add b? That means add a b. That means contents of b are added to a. That is the meaning. So here also another. So it is from the accumulator only the data is sent out or sent out to an output device or received from the output device to the microprocessor. That's what I told you. In and out operations are performed only on accumulator. This is the importance of accumulator, which is denoted by A. Accumulator denoted by A. So here I have shown you, this is your accumulator. It is an 8-bit register, D0, D7, D0 to D7, 8-bit register. And I have given some more things in addition to the things that I have explained, shift operation, etc. There are also some interesting operations called DAA, decimal adjust after addition. This is also performed only on accumulator. And what is the disadvantage here? This accumulator is only a byte operation. That means all the 8 bytes of the data must be operated at once. Like microcontrollers, this is not bit addressable. That means you cannot access each bit, D0 separately, D1 separately. Suppose I have 8 bits of here, say for example 10, 110, 10, something 8 bits assume. If I want to change the contents of these bits, I cannot change one single bit, either this or this or this. I have to change the entire bit. That is a byte. You know that 8 bits is 1 byte. So entire data must be changed at a time. That's why we say accumulator register is not bit addressable. It is always byte addressable in the microprocessor. This is also another disadvantage in this microprocessors, right? So I have given the example here which I will explain. For example, add a comma b. That means the contents of b register are added to a register and the result is placed in a only. Very important. Rotate accumulator left. See here you are using only accumulator. I am not using the other register. Like this, many of the 8085 instructions are accumulator based instructions. This is the architectural feature of CISC processor, which I have explained repeatedly. So this is the importance of understanding architecture. Next is temporary register. It is an 8-bit register. So you know what is temporary. So there is a temporary register provided, but it is not accessible to the user. That means that you cannot move the data into the temporary register. This is a totally internal. The ALU will take care of this, or CPU will take care of this. You cannot do this. But when do we use this? Suppose I want to, here I have given one example, move immediate MVI. You will understand the instructions in the next coming classes. Don't worry. For the present, you understand MVI means move immediately the memory M and data. So here we want to move a data 17 H means hexadecimal data into memory location. So here what we do, first the data will be moved to, that is the opcode of the move immediate M, and here how to tell these things to the microprocessor through your operational code, as I've already told you. So we'll get this from the instruction register operation code, the meaning of this. Then first, where do we move this 17H? The 17H will be moved to the temporal register. From there we'll move it to this, as we cannot directly move the data here. So similarly, suppose I want to exchange or interchange two data operands, that is, say for example, exchange A and B, for example. So if I want to exchange the data, that is move the data of A to B and B to A, then what we have to do? We need some temporal register where the data in the B is moved to the temporal register. Then A data will be moved to B, and then temporary data will be moved to A. So for such purposes, we use this temporary register. That is temporarily, that is this intermediate data will be stored. So here I have given further explanation. So in arithmetic and logical operations that involves two operands, the accumulator provides one of the operands here. The other operand is provided by the temporary register, as I have told you, while performing logical operations to find out the greater or smaller or swap or exchange, etc. We use this temporary register. Here also I have given one example. So add C. So when I consider add C, what is this default register? A, as I already told you. Add, actually the meaning is add AC instead. So C register contents are moved to the temporary register, and then addition of A and temporary register will take place. So this is, and finally the result will be stored in A. This is what is called as temporary register. Now we have a flag register. So a flag register is also popularly known as status register. Status means it will denote the status of the ALU. Some people also call this as it denotes the status of the CPU, but actually it denotes the values after arithmetic and logical operations. That's why the better thing is the status of the ALU is known by the status register or flag register. Why do you use the word flag? Flag means, 1 bit. So when I raise the flag means 1. When I flop the flag means 0. That means it indicates the status, either set or reset, either yes or no, like this flag. That's why it is also called flag register. As it indicates the status of the ALU, it is also called status register. Flag register is basically, as I have told you, 8-bit register. It has 8 bits, but out of these 8 bits, we use only 5 bits. So in the higher process, they use the remaining bits. That's why people also call this as they are reserved or used for future purpose. They are used or reserved. So among these 5 flag bits, now what are these 5 flag bits? So to understand this, the first one is sign flag. So when you consider the sign flag, as the name here, I have shown the diagram also. So sign flag, 0 flag, it is not, X means not defined, auxiliary carry, not defined, P means parity, CY means carry flag, parity flag, auxiliary carry, 0 and sign. So the remaining X, this one and this and 3. So they are not defined, that is undefined. They are not defined in the 8085. Probably they may be used for other processors like 8086 or some other processors. So we'll consider only now 5 bits of this. So what is this flag register? As I have told you already. So flag register is also known as status register. Let us consider the first one, sign flag. So what is the meaning of sign? So normally we have 2 types of numbers. One is signed number, the other is unsigned number. Unsigned means by default it is always a positive number, but we come across negative numbers also. That's why we always use a sign. So this sign will be normally given by the bit 7 MSB of a number. So whenever you come across a negative number, or whenever this D7 is 1, after performing an arithmetic or logical operation, this bit will be set. That means this bit will be made 1. That is, this flag will be set, or this bit will be set. That is the meaning. For example, in a given byte, if D7 is 1, that is the meaning. D7 means the MSB, this bit. last bit. Here you can see this is D7, D0, D1, D2. Remember, in the digital it won't start with 1, it always starts with D0, D0, D1, D2, D3, D4, D5, D6, D7. D7 means actually it is the 8th bit, that is MSB also. So when you consider this D7, if it is 1, the number is treated as a negative number, very, very, very important in a signed number system. That's why in a signed number system, when I consider 1, 1, 1, 1, 1, 1, 1, 1, all the ones, this 1 indicates the negative. Therefore, you will have only 1, 1, 1, 1, 1, 1 for magnitude. That's very important. If it is 0 means automatically it is taken as a positive number. This will be automatically done by the ALU during the arithmetic or any other operations. This is a very, very important thing about sign. It indicates the sign. Nice. Next, 0 flag. As you know, this is 0. That means when you perform any arithmetic operations, if the result is 0, then the 0 bit will be set. That means this this bit will be equal to 1. When this will be equal to 1, whenever an arithmetic operation gives a 0 result. So for this I have taken one example here. You can see, suppose A is equal to 0, 1, 0, 1 and B is equal to 0, 1, 0, 1. You see, both are equal, similar numbers, identical. Suppose I perform an addition operation. So when I perform addition on these things, it will not be 0. Therefore, the Z flag is not set, rather it is reset. Suppose I perform a subtraction operation. Here you can see subtract A comma B. As both are equal, then result is 0. So once the result is 0 means the Z flag, 0 flag will be set to 1, which indicates that the result of this arithmetic operation is 0. And this flag is also widely used in jump instructions like jump on no 0 to take any decision, JNZ jump on no 0, JZ jump on 0. That means when you want to make some loops or branching conditions, then if the result of an instruction is 0, then go to the target location, that is execute some other instruction, otherwise execute the next instruction. JZ jump on 0, this is the use of 0 flag. So 0 flag not only represents the status, it also controls. That's why these bits are also called sometimes control bits. Some of them will indicate the status, some of them will indicate the control, some of them will help in controlling the execution, normal execution of a program. That's why some people also called these bits of the flag register as control bits. This is very important. Jump on no 0 if the result is not 0. Jump on 0. Similarly, when you consider auxiliary carry bit. So what is this auxiliary carry bit? If you take up this again, AC. Here you can see AC. AC means auxiliary carry. What is actually the meaning of auxiliary carry? Auxiliary carry means addition, helping, extra. So already you have a carry bit. In addition to this, I have another carry bit called auxiliary, additional or helping. So this is an extra carry bit. So when do we use this? This is the most important bit that will be asked in the examinations also. This carry bit, AC, auxiliary carry bit, used in only BCD arithmetic operations, binary coded decimal. BCD means binary coded decimal, where the value is maximum value is only 9. So if I take 8 bits, I say 1001 9 10001 9. This is 0110 as you know. So this is 1248 as usual. 4 plus 2 6. This is also. So 1000. That means this will be your 68. This will be your 99. 68. How do you 68 this? This you know that this is 0101. This is 4-bit BCD. What is its value? 1 1248. That is the code, as you know from digital electronics. 1248. 1248. But 0 means 0. 0. 8 into 1. That is 8. This is 0. 2, 4, 0. That is 4 plus 2, 6. This is 9, 9. So this 4 bits indicates the 9, and these 4 bits indicates the 9. That means the first number is 99, and this is 68. When we add these two, you see here 1 plus 0, 1, 0, 0, 0, 0, 1 plus 1, 1, 0. This is, I have a carry 1. So whenever there is a carry from third bit to fourth bit, whenever there is a carry from third bit to fourth bit, that's what we write here. Whenever the carry is generated by the third bit and passed to the fourth bit, very, very, very important, then this auxiliary carry flag is set. This is the meaning of AC auxiliary carry. Remember, this is used only in BCD arithmetic operations, and this AC is normally not used for conditional jump instructions. Just now, as I've explained earlier, carry, jump on 0. Like this, we cannot use. This is only for BCD operations. That you should remember. This one, another very important thing. And in the examinations, normally they give one simple question that in which operations the auxiliary carry is affected. Only during BCD operations. I think the example is clear. Now, after this, parity. What is the meaning generally parity? In mathematics, so we try to use this parity to check whether it is an odd number, given number is an odd number, or given number is even number. Same thing here also when you have binary numbers. Based on the number of ones, we will decide whether it is an odd parity or even parity. For example, here if you see, if I have some number, say 10110, something I have taken a number only to explain this. So how many ones are there? 1, 2, 3, 4, 5, 6, even number. So it has an even parity. When you consider this byte of data, so let us see here how many? 1, 2, 3, 4, 5 only. That is, it is an odd parity. 5 means odd, 6 means even. Therefore, if I am checking the even parity, so I write 1 for this and I write 0 for this because it is an odd parity. This is even parity. Sometimes this may use to compare the numbers, especially this parity is used in serial communication. They call this as parity bit. So you will understand these things in future. So similarly, this is also used for control applications. That is, this will be used along with the jump instruction, JP, jump on parity. If the parity bit is true, jump to the location indicated by the target address. Jump on no parity. If there is no parity, you jump. Else, you continue the next instruction. This is called parity or parity flag or parity bit. So as you know, another most important, which is very, very popular, that is carry flag or carry bit. What is this carry bit? This carry bit is whenever you perform an arithmetic operation on two numbers, if there is a carry, that is from MSB next to the next bit, then when this instruction is executed, there is a carry bit at the MSB. Then the carry bit will be set. This is very simple. To make you to understand, I have taken an example here. You can understand here. So this is an 8-bit data, binary data. 1101, 1001, 1110, 110. Suppose I add these two. So 1 plus 1, I get a 1 here. So 0, 1, 1, 0. Similarly, 0 plus 1, 1, 1 plus 1, 0. Here we will have a 1. Then 1 plus 0, that is 1 plus 1, 1, 0. That is 1 plus 1 plus 1, 1, 1. 1 plus 1 plus 1. Carry here it was. So 1, 1. That is, I have a carry 1. See, I have written. And the remaining data is sum. So this is normally called a sum. This is called carry. So by adding these two numbers, I got a carry. That means once you get like this, immediately the status flag will raise the carry bit. So which you have already seen. So the first one was carry flag bit. I'll show you once again. So this was CY, carry. Some people call this as C and some people call this as CY also in some of the process. So this bit will be set. That means this bit will be made equal to 1 whenever you have a carry. Say carry. So this is also widely used in along with jump instructions, that is jump on carry, jump on no carry. So that means in any program, if the earlier program, in the earlier instruction, if there were a carry, jump to the indicated target location, else go to the next. That means after addition of two numbers, if there is a carry, you would go to some location and execute that. This is normally, it will go to a subroutine program that we will consider in the next coming classes. At present, you just understand the meaning of what is the carry flag. Okay, you have understood various registers, you have understood what is ALU and what is the Intel 8085 architecture. I hope this is helpful to you. Good luck.